Welcome back to this series of videos in which we are solving the precipitation exercises. In this tutorial you are going to learn how to use Python tools to visualize and analyze randomly generated data. The purpose is to get acquainted with statistical concepts such as probability density functions and cumulative distribution functions. It's important to remember that this notebook or this class you should do this class before exercise 5, because in this class we're getting introduced to concepts such as cumulative density function, probability density functions that we will use in exercise 5. As usual, in the folder with the exercises, we get into notebooks, and you have two notebooks. One is called Statistics Basics Fitting Distributions, and the other one is the same name with incomplete. So one is completely solved and the other one has gaps that you can fill during the class. I'm going to start with a new notebook. For that I just click here on plus and then Python 3, and we can rename the notebook. Let's call it Statistics Basics Video. Good. First thing, as usual, is to import packages. Import NumPy. Then we're going to use from SciPy all the statistical tools, stats, and then to create plots, we're going to import matplotlib. And Seaborn. This is basically what we always import. In this notebook we're not going to use pandas, that's why I didn't import it. Just shift enter, and I did something wrong. Notebook. Good. You can just simply, as I told you in other videos, drag and drop this, because these are the usual. So this is exactly what we did right now. Okay. So we're gonna work with the normal distribution, which is the typical Gaussian bell. So you can example normal distribution, and we're gonna start by creating random values. Generate random values. Basically we're gonna create a vector of random values extracted from a normal distribution. How do we do that? We're gonna use NumPy, and there's a function called random, and in here we call normal distribution. We have to define two parameters of the normal distribution. One is the mean, which in Python is called log, so the normal distribution with mean 0, and standard deviation, which is called scale in Python notation, with standard deviation of 1. And we have to input the number of values we want to create. So let's say we want 1,000 values. This will create a huge vector with 1,000 values. We can save this as x random. Okay. There is something very important, is that we plant a seed. So these supposedly are random values, but they're pseudo-random values. So for all of us to get the same results, we're gonna plant a seed. This means that all the values that we get, even though they're random, they're gonna be equal for all of us. So we plant a seed with, you can put any integer here. I'm gonna plant 0, and if you do the same, you get the same results as me. Good. We have created our values. So let's now visualize what we have here. The easiest way to visualize our data is an histogram. There is a function called plt in matplotlib, histogram, and you can just need to put the x and the number of bins. Let's say 20. Oh, sorry. This will be x run and you create an histogram. But there's a much better tool, so you don't need to do this in Seaborn. So sns.distplot, and this create a better histogram. So we just import the random values, and then we set here false. We'll see later on what this KDE means. With this, we have created a histogram. This visualization is very sensitive to the number of bins in which we divide our data. This is the number of columns. This plot calculates what it thinks that is the best number of bins, but we can change it. To change it, we can copy this here and input the number of bins. Let's say, for instance, 20. So you see that the plot has changed, and you can play with this and give different number of bins. Maybe I input it too many here. So 100. This means that the plot is sensitive to the number of bins, and that's not a good thing. Instead, we can copy again. This plot allows us to plot or creates a soft line that best fits our data. So for that, we can only need to import this, and this will create the first histogram. You see this histogram is exactly this one, but now we have a soft line that more or less fits our data. This is the KDE, kernel density estimator, that if you check the help, you see that by default is true. So if this is true, we are creating this line here. If it's false, like in the first plot here, we don't create it. Okay. This is just for you to more or less guess what is the shape of the distribution you are working with. In case you know that what is the distribution, like in our case that we created the values from a normal distribution, you can simply feed the distribution and plot it here. Like so, again, x random, and then we tell we want to feed a distribution, and we know the distribution we want. So we get into stats. Important, we have imported from SciPy all the statistical tools. Inside here there are plenty of distributions, and now we want the normal, so we can put NO, and we see how stats call the normal distribution, stats.norm. So we're gonna feed a normal distribution, and let's again say switch off the kernel estimator. So now we know we have our histogram, and on top of that we have our fitted normal distribution. Interesting, you see that there are some kind of corners here, but the normal distribution is much softer. Okay, so it's a continuous and derivable function. Let's fit our data, or let's learn how to fit our data. Distribution fitting. Okay. Now we're going to use the statistical tools in SciPy, which is SciPy.stats, to feed a distribution to our data and to learn what are the probability density function and the cumulative distribution functions. To fit our data, we only need one function that is called fit. So first we have to tell the distribution function. In our case is statsnorm, remember, same as here, but it could have been many other. We'll see in the following exercises the gen extreme. Okay, but there are plenty of distribution functions, but the idea is always the same. Stats dot the distribution, in our case is norm, and then we call fit, and with this we want to fit the parameters in the distribution. We have to input our values, and this will give us two values here, two parameters. What are the parameters of the normal distribution? Mean and standard deviation, which in Python are called location or log, and scale. So we have just fit our distribution scale. Interesting, we have created our values from a normal distribution with mean 0 and standard deviation 1, And once we have fitted the random values that we created, we get a mean of practically 0 and almost 1. So the fit is not perfect because our data is not perfect. Okay, so now that we have fitted our distribution, we are going to learn how to use it in 3 different ways. The first will be the probability density function called PDF. Okay. The probability density function represents the relative likelihood that the variable takes a specific value. That means that values with a higher PDF are more likely to happen. To use the PDF in SciPy.stats is very simple. We only have to call stats.norm in our case .pdf. But first we have to create a series of values in the x-axis, which is this one here. So let's create linearly spaced values of x, and to do that we're going to use numpy lin space, and we have to input a starting point that we're going to use, for instance, -5, and stop point that is going to be something like 5, and we want some number of, let's say, 100 values. So this creates a vector with 100 values linearly spaced between -5 and 5, and let's call this x. Okay, now we want the probability density function for each of the values inside x. So what I told you before, we just call our distribution, which is stats norm, and we call PDF. We give the values of the x, and then we have to set the parameters of our function, which are log and scale. So we must have first fitted the distribution here to know which is log and which is scale. And now we get 100 values of the PDF for each of the values in x. Let's save this as PDF, and now we can visualize. And let's plot it. So plt plot, and we plot x against PDF, and let's give it a color black, and give some label to the axis. So the x-axis, we'll just call it x, and the y-axis, let's call it PDF. Okay, semicolon, and we plot. So this is our PDF. This is exactly what we got here. Okay, so this black line, we have just created our own black line, but they're both equal. Good, that was the first use of the distribution, the probability density function. So what I told you before, the higher the values of the PDF, the more likely the value. So the most probable value in this normal distribution is 0 with a probability density function of 0.4, and values below -4 or over 4 are very, very unlikely to happen. The next use of the distribution will be the cumulative distribution function, also called CDF. This function is the probability that the variable x takes values lower or equal than a specific value. For that reason, it's also called the non-exceedance probability. It is the integral of the PDF, so it's the integral of this function here. It's an always monotonic increasing function, meaning that it cannot decrease in any point in the function, and the maximum, it has to range between 0 or 1. If you get a CDF with values over 1 or below 0, there is some error in your calculations. To calculate the CDF, it's pretty simple. So we get into stats norm, and we call the CDF function. Then we give values to the x-axis, and same as before, we have to set the parameters, which are log and scale. And we're going to create a vector with 100 values. These values should be always increasing, and let's call it CDF, and we can plot it. We can copy this here, and put it here, but change here CDF, and here CDF. We can just say that this is equal to the probability that X is lower or equal to capital X. Good, and this is how it looks, the CDF of a normal distribution. Remember, this is the integral of this distribution here. It starts at 0 and it ends in 1. And it has to be always an increasing function. The meaning of this function will be, for instance, a value X has a CDF of around 0.5. Means that the function will take values below 0 with a 0.5 probability. For another example, values of 4 has more or less one value of 1 for the CDF. This means that almost always the variable will take values below 4. And now we're going to use the last use of the distribution function, which is called the percent point function, or PPF. This is actually just a use of the CDF. So in the CDF, we're starting from the x-axis, we go up, and we give values of the y-axis. And now we're just going to do the opposite. We're going to give values of non-exceedance probability, get into the CDF function, and extract the x value. So let's create a linearly spaced values of CDF. Let's call it CDF underscore, and we use the same function as before, linearly space. It has to start at 0, as we said before, and stop at 1, and let's create quite a good number of values, so 10,000 for instance. And now we're gonna calculate X, okay? Let's call it X underscore, and we're gonna use the stats norm as usual and call PPF, and we input this CDF underscore, and the same as always we have to set the parameters, which are log and scale, and create a plot. We can just copy it here and make sure you change this into X underscore and CDF underscore, and we get a similar plot. Okay. The only difference is that to create this plot, we define a linearly spaced values of X, and we calculate the y-axis using CDF. And in this second, we did the opposite. We defined a series of values in the y-axis and used PPF to calculate its x-axis corresponding value. So now, why am I teaching you all of this? Use of the CDF. So basically we're going to use a lot the CDF and the PPF for two reasons. One example is if we want to know the probability that the variable X takes a value lower than, for instance, X equals to 1. So this will be the first problem. Probability that the variable X takes values lower than, for instance, 1. Okay. This needs the CDF, so we want a value of 1, and which is the probability that the function will take values below it. So we just do it. We start here at 1, go to the function, and extract this value here. Let's do it. So CDF for a value of 1 will be stats norm, we call it CDF, and now we just want the value 1. We don't need to import a vector, and as always, the parameters. And let's see what it says here. So 0.85, sorry. What does this mean? So let's copy this here again. Let's plot what we're doing. And now we're gonna put here a few more lines. So let's create a vertical line at value x equals to 1, and it's going to start from 0 to CDF1, and then let's give it a style. So this is going to be a dotted line, and now we can copy and put here. Let's create an horizontal line that starts at CDF1 and then goes from -5 to 1, and the same line style, which is a dotted line. And let's plot this. So this shows us what we've done. So we have our CDF that we fitted with the log and the scale parameters, and we input a value of 1, we get into the distribution, and we get out from the y-axis, and this gives us the 0.85 here. This means that the distribution will take values below 1 with an 85.5% of the time. The second use of the distribution will be to calculate value x that is not exceeded 99% of the time, for instance, of the time. Okay, to do that we need the PPF. So now we're gonna input in the y-axis and output in the x-axis. So x for a 99% probability. As always, stats norm, and we need the PPF. We define a value of non-exceedance probability, which is 0.99, and then the parameters of the normal distribution, scale, and let's see what's our result. So our result is 2.25. Let's see what we're doing. So we can copy that and paste here, and we're going to change this here. So this is going to be a vertical line that starts at x99 from 0 to 0.99, and the horizontal line should start at 0.99 from -5 to x99. Okay, so now we want the value of x for a non-exceedance probability of 0.99. So we start here, intersect with the CDF, and exit through the x-axis, and we get the 2.25 value. This means that the variable will take values below 2.25 with a 99% probability. And this is all for today. Here at the bottom you have a useful link with a Seaborn tutorial in which it tells you how to do the histograms, etc., the kernel distributions estimator that we didn't get into in the video, and some other stuff kind of interesting. Later on it will get into bivariate distribution. You don't need to care about this. Thank you, and for any questions just write me an email or on Moodle.